So the topic today is global nonlinear stability of Minkowski space for massive fields. So in the last lecture, I mentioned roughly the result that we want to prove today. I'm going to state the results more precisely and give you the outline of the proof, but I'm not able to, even in 2 hours, to tell you all the details of the proof. The global existence problem that we ask for the Einstein equations is based on the study of self-gravitating massive scalar fields. So earlier results along the similar lines with similar techniques were only able to cover massless scalar field. So here, as I explained from the beginning, I mean in the first, actually in the first lecture, I'm interested in putting matter terms in the modeling, in the problem, and understanding the effect of matter terms. And that's what we have done in the previous lectures as well. The choice of gauge that we will use is a so-called wave coordinate gauge, where the coordinate function satisfies wave equations. And the main result will be indeed a global existence result close to Minkowski space. So you take Minkowski space, take a slice, some hypersurface in Minkowski space, introduce some perturbation. The perturbation will be determined by the matter. You put some matter in some compact place in the space-time, and you study the global dynamics of this bump of matter. That's what we want to do here. The method of proof will be based on foliation by hyperboloids, which is a new method of analysis to understand quasi-linear wave Klein-Gordon systems. What is important here is that the frameworks that I will discuss give you sharp rate of decay in time for the solutions, and that's essential. Without this sharp decay, you won't be able to cover this effect, to understand the effect of the matter, at least not globally in time. The foliation by Minkowski, the Minkowski space by hyperboloids is something we are going to use. So let me outline the lectures for today. So there will be first general strategies that I will explain, and I will especially explain this for simple models to begin with. And slowly you will see that the techniques were built to cover, first to cover models without any interaction at the level of the metric. Then we had a hierarchy of models, one involving what I have called weak metric interactions and strong metric interactions. And eventually understand the Einstein equations where you have strong metric interactions, meaning that there are coupling terms between the Klein-Gordon field and the metric. So such terms arise in the Einstein equations. And in addition, you have something called the quasi-null condition, which has also to be understood. So the outline is like this. We look at the general strategy. We we state the main result for the Einstein massive field system. And in the last part, I will give you some details about the proof. And again, I will only be able to do it in 2 simple situations. But the last one is rather close to the full Einstein system. But of course, there are some additional problems that I will discuss very briefly in the end. All this work is based on a joint papers with UMA. And we had a book more than a year ago, and then a paper where we study a simplified model deduced from the Einstein equations. And the full result was given in this preprint. A week ago, there was an alternative proof by a different method given by Kyun Wang and Jiwa Wang, also proving the global existence of Einstein equation for massive scalar fields. There is also a work in a different direction, but also using hyperboloidal foliations by Feijman, Jodieu, and Smoulevici. And maybe a last result I can mention is an ongoing work also that I'm doing with UMA, where we use these ideas and we deduce the nonlinear stability of Minkowski space, again for self-gravitating massive fields, but in a different situation where instead of the classical Einstein theory, you look at the modified theory based on, you remember that I have presented that in the beginning, that you replace the Hilbert-Einstein action in the Hilbert-Einstein action, you replace the scalar curvature by a nonlinear function of the scalar curvature, which is something close to R. It's a R plus a quadratic correction. So we have also a result in this direction. And let me start with the simplest possible model. Everything here will be about systems of nonlinear wave Klein-Gordon equations. And the simplest model you can think of is you take the wave equation, you take the Klein-Gordon equation, and you add as a source something quadratic at the level of one derivative. There are many models in mathematical physics that are taking this form, and they usually describe fields that are, some will be massive, some will be massless, and you have products between them. The massive Einstein equations is of course the model that we want to treat, and as I just said, the modified gravity theory is also part of this set of models. But there are more models, so you can also, even without the Einstein equation, you can look at Dirac, Klein-Gordon. There are other, many other equations that have this form. So what's the objective here? So the objective is to solve the Cauchy problem, to show global existence for the Cauchy problem, global in time, starting with small initial data. So for us, it would be small data close to Minkowski space in this case. To study such systems of nonlinear wave equations, you have the so-called vector field method, which is based on the conformal killing fields of Minkowski space. So instead of the usual L2 norm, you define norms that are adapted to the geometry, and they are defined by differentiating the equations by using these killing fields of Minkowski space, or conformal killing fields. So this goes back to work by Sergio Kleinerman in 85 and following years. So you have suitably weighted energy estimates, very well suited to your problem. The Sobolev inequalities, for instance, must be adapted to these new norms. And the whole proof is based on the bootstrap argument. And we will see one or two or three examples of that. The nonlinearities for this theory have to satisfy the null condition. So typically you can think of this a product like that, nabla alpha u, nabla alpha v, where you are using the Lorentzian metric to compute this product. And to do the proof, you have to find time decay. So you have to show that enough decay is taking place and get good bounds. Typically, you want to be able to integrate in time some error terms and show some interaction terms and show that they allow you to get a good control of the energy. The derivatives that are tangential to the Lie cone have typically better bounds. And in this direction, you have an extensive literature, first of all, on nonlinear wave equations, so without any Klein-Gordon terms. So this goes back to all these people. Later, the so-called Strickhart's estimates were derived. So these are space-time estimates that control, in a stronger ways, solutions. And these techniques allows a number of people to attack the Einstein equations. And what was done in all these works was a treatment of Einstein equation with a massless scalar field, and typically either get local existence, optimal result of local existence, or get the nonlinear stability of Minkowski space. So this was the pioneer work by Christodoulou and Kleinerman in 93. Now, for nonlinear Klein-Gordon equations, you have also a number of works, but some are much less. And there are even much less works if you want to couple nonlinear wave equations and nonlinear Klein-Gordon equations. There are almost, very little work on this problem. And the reason is that there is a smaller symmetry group. If you now allow the Klein-Gordon, some Klein-Gordon field in your problem, you can no longer use this scaling field. So the presence of the mass term in the Klein-Gordon equation prevent this quantity to be a killing or conformal killing field for the problem. So you have to devise a method which doesn't use this. But if you don't use this, the norm that you can define, this weighted L2 norm, are much weaker, and you cannot close the argument. So of course, if you would only look at the Klein-Gordon equation, not the wave equation, it would not really be a problem because you have more decay for Klein-Gordon equation. The mass term is a good term, it gives you some dissipation, and so you get better decay for components of Klein-Gordon equation. So if you're interested either wave equation or Klein-Gordon equation, but somehow separately, things works very nicely. But otherwise, if you want to understand the coupling between these two equations, you need a different technique and something that is more robust. Is going to use, so the basic point is that you cannot use this field here, and you have to work with different norms. So this was recognized by Georgiev and Katayama some years ago, and these people introduced certain assumptions on the nonlinearities. So in the end, of course, it's going to depend on the assumption that you make on the nonlinearities in your problem. And so very strong assumption, meaning that you prevent certain products to exist in your system. So under this condition, basically the same techniques as before could be applied, and Katayama were able to find slightly weaker conditions to handle a coupled system. But it's only with the method that I have introduced with Yuma that we could start solving this problem under very weak assumptions on the nonlinearities. I also want to mention many earlier works which are using hyperboloids for a different reason. And in particular, there was this work by Helmut Friedrich, who was able to prove global existence for the Einstein equations using a conformal transformation, Penrose compactification. So the method is rather different. There is also similar work by Dimitri Christodoulou in '86. And the other works are not concerned with the Einstein equation, but Hermander and Kleinerman here were interested in Klein-Gordon equations, not the coupling, but just looking at the Klein-Gordon equation, possibly nonlinear, and deriving sharp or almost sharp rate of decay in time for solutions. And in fact, the method didn't really give the sharp rate. So for instance, this paper were able to produce 5/4, which is not the optimal one. And the final remark I want to make here is that numerically, these hyperboloidal foliations have been very much used. And in particular by Vince Moncrief and some other people here. So it has been recognized as an important tool numerically to solve the Einstein equations before. The hyperboloidal foliation method that we propose here is just based on this observation that you have fewer conformal killing fields and you should not use a scaling vector field. The strategy is to introduce a foliation of Minkowski space by hyperboloids. And one reason why these hyperboloids should be good and should somehow give you a better control of the solution is that these quantities are fully geometric. So you take a point in your spacetime and you look at surfaces that are constant distance from that point. That's the way you define the hyperboloids. And therefore, these hyperboloids does not require much additional information. They are fully geometric objects. They are generated by some vector fields, which are called the Lorentz boost, or space-time rotation. So these vector fields are going to play an important role everywhere here. So we will use this LA is XA dt as T dxa. So we will use that, and maybe I can say immediately that we will also use the translations. So these from 0 to 3, so this reflects the invariance of Minkowski space by translations, and this quantity are called a boost, and they correspond to rotation in space and time, as you know. What we want to do here, we want to revisit the standard vector field arguments, but we are going to use norms, new weighted norms that are adapted, well adapted to the Minkowski geometry. And in particular, you will see quantities like that, the hyperboloidal energy that you can define on an hyperboloid. We will write Sobolev inequality like it was done before, but these Sobolev inequalities will be expressed on hyperboloids. and so we have to look at what vector fields are rising in these inequalities. There will also be an RD type inequality and many more ingredients. And the strategy that I had here was to successively cover more and more complicated system, adding more and more nonlinearities. So the simplest situation, of course, is to revisit, and I will show this in some detail. So at some point you will really see very concretely the proof. So I will do that later in the third part. Just look at a nonlinear wave equation with null form, even forgetting about the Klein-Gordon contribution, right? Just a wave equation. And it's interesting to redo the proof. Then I will tell you maybe just a statement about the system with weak interactions. In a sense, you will understand, you will see in a minute. And then we will move on to system with strong metric interactions and null forms. And this is therefore relevant to understand the Einstein massive field system, where you have such terms, and you have also null terms, but you have also terms that I have called quasi-null terms that are not immediately good terms, but yeah, they can be treated, but for different reasons. Okay, so this is a starting point. I define the hyperboloids. So you look at the t positive part, and you simply write that the Lorentzian distance t squared minus x squared is equal to some constant. And S represents the hyperboloidal time. And I will typically, what I will do, I will often put the data on hyperboloid, so for some fixed S0. And you will see in a minute that I like to take everything bigger than 1, so in order not to have degeneracy at the origin. The foliation, so this defines the foliation, and especially a foliation of the future light cone that we take from the origin at time 1. Okay, so I give you a picture in a second. So this K is a light cone from the point T0, 1, 0. Okay. You can easily, from these inequalities, you can easily see that the time, the standard time, is greater than the hyperboloidal time, and it's also bounded by S squared. So you can see the comparison between the standard time and the hyperboloid time with this inequality. And this is a picture. So I hope you can see. So there is a light cone. I mean, there is a bound here, a light cone from the origin, 0, 0, and there is another light cone from 0, 1. And all the hyperboloids that we can plot inside will be somehow cut by the second light cone. The light cone from 1 is intersecting all these hyperboloids. What we will do, typically, we will integrate. So this will be the regions, typically, where we want to study our space-time. Of course, the initial data can be put at any time. So we will typically put our initial data set at the time S0. So think of a slice t equals S0 located like this. And we will put initial data in this set here. Okay? So localize initial data. And we want to understand the propagation of this initial bump of matter. So the matter would be here. And of course, by the finite speed of propagation, it cannot exit this cone that we have introduced here, the cone K. Okay. So the method will proceed by doing energy estimate, like it should be done, limited by 2 hyperboloids. So usually that's not what you do. I mean, usually you have 2 slices, t equal constant, and you integrate between 2 such slices. So here that's the way that we will proceed here. So we have a region like this, limited by 2 hyperboloids, and we are going to integrate and write energy estimate in this region, where the initial data is put here and propagates, and therefore on the boundary here, we always would have 0, right? So there is nothing can leave from this boundary. The vector field that we will use will be the Lorentz boost that I wrote on the blackboard already, and the translation. And the analysis will usually be done in something I call the semi-hyperboloidal frame. So we need a frame of vectors. And so what we will do here, we will use d bar 0, which is just dt, right? So we are not using ds. ds would be something that I will call the hyperboloidal frame. But here, for some reason, it's more convenient to keep t for the time, dt for the time. And the second vector will be, or set of vectors will be d bar a, defined by taking the Lorentz boost and normalizing by t. So this will be xa over t dt plus dxa. For instance, if you decompose the wave operator in flat space, box U, right, that's what you get. So it's just an easy calculation that you get 2 time derivative of U, you get a lower order term dtu times this coefficient here, you get cross terms d bar 0, d bar a, and you get the Laplace contribution here on using the d bar a vector fields. Okay, so that's just a calculation. I just gave you everything. You can check this. And in particular, maybe observe that there is a factor s over t that comes here in front of the second time derivative, and this is something that you will also often get in the rest of the analysis. So we are going to use an energy on these hyperboloids, and this energy corresponds to certain weighted directional derivatives that are suitable for the problem. And something I must emphasize is that we are really going to use a full expression of the energy flux on the hyperboloid. So we don't lose anything in the analysis. And to be a little bit more clear here, let me give you the example where I take a linear wave Klein-Gordon equation. So box u minus c square u is f. Takes a linear Klein-Gordon equation in Minkowski space, right, in a flat space. So this is a simpler situation. And if you recall this notation here, this is a form of the energy. So the energy is found to be s over t square dtu square. So you can think that you have this additional weight in front of dtu. And then there is a sum here of term like this, and there is a Klein-Gordon term. So if you express, so this is just a calculation, right? Take the flux, hyperboloid, you have your energy corresponding to the wave or Klein-Gordon equation, and you compute what is a flux on an hyperboloid. This is what you get. But you can also express it in terms of this frame, right? So in terms of this frame, you have a coefficient s square plus r square. So there's a good term here, the time derivative of u square, and you have the d bar a u square term, and the Klein-Gordon contribution. So we will play with this, we'll differentiate the equations, etc. That's the goal. So let me summarize the features of the method that we have to develop now. First of all, we base everything on the invariance by Lorentz transformation. So we have the foliation of Minkowski space by hyperboloids, which, as I said, are level set of constant Lorentzian distance from some origin. In the norm that we define are invariant under Lorentz transformation. I also want to emphasize that the hyperboloids are all asymptotic to the same limiting light cone and approach the same sphere at infinity. So in a certain sense, no energy can escape through null infinity. You can imagine a different foliation, but the foliation that I have here on this picture has these properties, that all these hyperboloids are asymptotic to the same light cone at infinity. We are going to use a small set of Killing fields, right? So this will not appear except for some statements, but certainly not to differentiate the equation. And this is a key to be able to handle Klein-Gordon equations. And we'll be able to apply this technique to Einstein matter system when the matter model is not conformally invariant. So that's the point. Klein-Gordon is not conformally invariant, and you have to do that. So one important point for the method will be to derive estimates that are as sharp as possible. Okay. There will be always some loss. So you will see in the estimates, there is always some algebraic loss that comes in the estimates. But essentially, maybe I should say almost sharp decay rate in time should be obtained. And to do that, we need to control the interaction terms, and especially the ones that are related to the curve geometry. And sharp bounds will be obtained for nonlinear wave and nonlinear Klein-Gordon equations. So let me finish this introduction of the method, of the ideas, the main ideas of the method, by an example, and just a statement here. So I'm only stating a result here, which is a result that we had in our book. You take a system of equations like this. So box or Wj times, you have second order derivative here of Wj times some quantity g. You have Klein-Gordon terms, and you have a source involving W and one derivative of W. You fix some initial data for Wj and W and the derivative, the time derivative, and you define the problem on Minkowski space. Right? So of course there is an underlying curve metric which is Minkowski plus this. Right? So the real relevant metric is a perturbation of Minkowski space. But in any case, you can define your functions on Minkowski space and think of this as a sort of perturbation, if you like, but it can have some strong effect on the dynamics, of course, of the solutions. And in order to state the assumptions here, I want to split the indices. So if I goes from 1 to n prime, I will assume that Ci is 0. So this is actually a wave equation. And if I goes from n prime plus 1 to n, this quantity is bounded below by something strictly positive. So it's a genuine Klein-Gordon equation. And to that, I'm adding now some assumptions. And as the title suggests, I'm going to put strong assumptions to be in a so-called weak metric interaction case. So look at the form of this, right? The G here corresponds to the curve metric, and I will decompose the curve metric in a first order term in dW and a zero order term, W. And I will similarly decompose the source, Fi, as a product, dW, a product W, and a product WW. Right? And now I'm going to put assumptions on this. And the first assumption is symmetry properties. So there are two conditions of symmetry. There is one condition, so if you look at the indices, yeah, there are two ways to write a symmetry between these quantities. And the first condition here is imposed in order to have an energy for the curve metric. So you want this to indeed represent, if you do Minkowski plus that, you want to think of it as a curve metric. So there is a symmetry assumption to be imposed. But also, you want the coupling between the various equations to be somewhat consistent. I mean, to be able to produce an energy for the coupled system. And that's what I'm doing here with a different symmetry assumption. So this is not a problem. That, of course, arise in our examples. Then I use this notation. So I use U for the first set of components. The wave I call also them the wave components. And the second set of components, I call them the Klein-Gordon components. And they are defined from n prime plus 1 to n. And I call them V. So this is typically my notation, U for the wave components and V for the Klein-Gordon components. And now comes the main assumptions. The first assumption is a null condition, which will be satisfied for many examples, except the most important one, which is the Einstein equations. But otherwise, this null condition will be in order. But it's only required for the wave component, because the Klein-Gordon components have more decay, so you don't need them. The null condition for the wave components are expressed in this way. If I take a null vector like this, and I contract my coefficients A, B, P that came in my decomposition with respect to psi, that should be 0. Right? So it's a way to express that these conditions are good on the light cone. So we impose that for the wave components, not for the Klein-Gordon components. So far, so good. And now comes, the important conditions here. So there is one condition which I call structural condition, and essentially this condition is imposed in order to avoid blow-up, right? So there are examples, you can find a number of examples, and Fritz John, for instance, was probably the first to study that and construct solutions that were actually blowing up in finite time. So not giving you any global existence result. So that's, here of course I want to eliminate these terms. So terms like UDU, or UDV, or U squared, these are terms that have to be eliminated, and the conditions that I wrote here do the job. So now I arrive to the most important restriction, which I call weak metric interaction, and again tells you that some condition B, so B, if I go back, came in the decomposition of the curve metric, or the perturbation of the metric. So you had a term like this, and a term like this with a B. So this BW is multiplied by two derivatives in spacetime of W, and now I'm restricting this term. By certain conditions, so you don't need to look carefully at the indices, but the point that I make here is that I'm excluding metric terms which involve wave component, U, and two derivatives of the Klein-Gordon component. Okay, and that's a term that we cannot cover in this theorem that I state now, but of course need to be covered, will be covered in a class of strong metric interactions, and is required to understand the Einstein equations. But here we just look at a simple situation. So we consider the initial value problem for a coupled nonlinear wave Klein-Gordon system with weak metric interaction, as I explained. We take smooth and localized, compactly supported initial data on either we put that on a spacelike hypersurface of constant time, or we put that on a hyperboloid by the local existence, because data have compact support. This is completely equivalent. And the result is that there exists a global solution, provided the initial data in some Sobolev space is sufficiently small, and you have a data which is a solution which is defined globally. The proof is based on a rather involved bootstrap argument, and I will show the bootstrap assumptions in the next slides. They involve 3 levels of regularity. So you have to decompose and make sure you understand each component, wave and Klein-Gordon, and different level of regularity. And as I already mentioned, the whole proof uses a family of L2 norms, energy norms, but which are not based on the usual standard energy where you would control everything, all the derivatives. You have to work with this an energy based on our admissible vector fields, which are the translation and the boost only. So this is a statement of the bootstrap argument. So I'm not giving the proof here, but just saying, what energy bound you get, basically. So to state the energy bound, I fix a constant C1 bigger than 1, small epsilon. I fix a delta sufficiently small, and I formulate the bootstrap assumptions in a given interval of hyperbolic time. So S0 is the initial time, S1 is a time, and you assume that your solution is defined at least up to this time S1. So the local existence will be okay, and then you get a solution which is defined up to S1, and you want to show that S1 is infinity. And the strategy so the bootstrap strategy uses a hierarchy of energy bound stated for all our admissible fields Z, and stated differently for the wave component and the Klein-Gordon component. So now I'm going to show three sets of, so let me show the 3 quantity. So all of them are bounds on the energy, right? Various type of energy, and the energy can either be, it can be concerned with U or with V, the wave or Klein-Gordon components. You have a certain number of derivative in Z which have been used here. So for instance, so the first set corresponds to high order differentiation, then you go from 5, 4 to 3. And what you have to look at now is the right-hand side. So there is a growing factor S delta, and also the same here. This is growing less, and this is growing less, and this is uniformly bounded. So you have a uniform bound for these components U, and otherwise you have some growing quantity, but which is very slow in a sense. So these are the bounds that you have to postulate on a given time interval. And what you do for the proof, you show that if these conditions hold, then the same inequalities hold, but with C1 replaced by C1 over 2. Right? So the logic is clear. You start with a set of inequalities, and you show that something stronger take place. And therefore, you can continue the solution. I will return to that later on. So the observation I want to make here is that you have algebraic growth factors, but they are rather slow. They are expressed in this form. So delta could be taken as small as you want. Of course, this constant C would change. And what's interesting here is that there is a uniform bound for the low order energy of the wave components. Okay, so this is just an example where I'm not trying to show the proof of that here, but I will show proofs later on. So I'm now moving to the Einstein massive field system. And what I want to do, I want to state the result. That will be our first goal. So what we want to do here. So we want a new approach for proving the nonlinear stability of Minkowski space, covering massive fields. And as I said already before, the earlier works were for vacuum spacetimes, or massless scalar fields would just be easy to add massless field to a vacuum result. The first result is, of course, the result of Christodoulou-Kleinerman, which was fully geometric, using Bianchi identities, the geometry of the null cone. So there is a lot. It's quite heavy. I mean, the proof you will see, even though the proof I'm giving is still quite long, maybe 100 pages or something like that, it's actually much shorter than the proof that you can obtain by using fully geometric methods. But in the same time, they don't give exactly the same result, right? So, I mean, they give the stability of Minkowski space, but they don't give you the asymptotics for large times, the so-called peeling estimates. Lindblad and Rodniansky were the first to analyze the Einstein equation using wave coordinates, but they were using the standard foliation. And concerning massless models, I can mention work by Bierry, Zipster, and Speck in this direction. So let's write the equations. The Einstein equations with the matter is written as you know. The stress energy tensor of a scalar field has this form, nabla alpha phi, nabla beta phi. You have the norm of phi plus the potential, V of phi. And for V of phi, I'm going to take C square, phi square. So this is what will give us in a second Klein-Gordon equation. Klein-Gordon equation is obtained by box phi is equal to V prime of phi, which is C squared times phi. And what we do is we take a hypersurface in Minkowski space. We introduce a perturbation, which is given by, essentially given by the matter. The gauge is a so-called wave gauge. So I guess I already wrote this before in the first chapter. So this is a condition that comes by expressing box of x alpha is equal to 0. So that gives you a condition on the Christoffel symbols of your metric. And let me also remind you that if you want to solve the Einstein equation, you have to prescribe an initial data set, which is a Riemannian 3-manifold with a symmetric 2 covariant tensor field. So we have an M bar, G bar, K bar. We cannot choose this data arbitrarily, but they have to satisfy the Einstein's constraint equation. So you have seen that already a couple of times. So you have the Einstein equations here, and here I just remind you about the notation. The matter that we put here, T00, T0A, is computed from the stress energy tensor of a scalar field that I wrote in the previous page. So that's our setup. And solving the initial value problem means that we are able to construct a future development of this initial data set, which is a Lorentzian manifold satisfying the Einstein equations. There is an embedding that allows you to see M bar as an hypersurface in your spacetime with a given prescribed first and second fundamental form. The matter fields also have been prescribed on this hypersurface. And the formulation that we obtained by introducing wave coordinates of this form is a system of coupled nonlinear wave equations for the metric. Right, so we have a system like that. Of course, there's a matter effect that I didn't write here. But that's in a vacuum, actually. This would be just in a vacuum. And if I want to summarize that, so you get a set of coupled nonlinear wave equation plus Klein-Gordon in our case with the matter. And you also have elliptic equations, but we are not going to look at that because there are equations, also as you know, there are equations that you impose on the initial data and which are propagated. Right? So we can reduce the whole system of global existence for the Einstein equations with a massive matter field to a huge system of nonlinear wave equations and one Klein-Gordon equation plus source terms that are coupling all of that. And also this is written, of course, on a curve metric, which is the unknown metric of the problem. So I'm going to write the system in a few minutes, but first let me state the result geometrically. So the geometric formulation is like this. If you look at the Einstein equation for a massive scalar field, which takes this form, which is equal to the product of one derivative of phi and a quadratic term in phi, and box phi equal v prime of phi, which is in our case just linear in phi. You prescribe an initial data set satisfying the constraint equations, and you assume that this initial data set is close to an asymptotically flat slice of the vacuum Minkowski spacetime. To make this statement here, I would need to impose some decay assumption at space infinity. But that's not what I want to do here. What I want to do is to be a little bit more precise and assume, as I said before, that the matter is compactly supported. But to be compactly supported because of the Einstein constraint, you cannot formulate your problem with a compact region, matter located in a compact region, and put Minkowski outside. Right, there are no such solutions, as you know. So there is a tail which comes from the Einstein constraints, essentially, and the tail is of the order of the Schwarzschild metric. Right? So the way to formulate the problem is to put Schwarzschild spacetime outside a compact region and put the matter perturbation on a compact region, which is, in any case, everything is close to Minkowski space, right? It's not because I'm introducing Schwarzschild that I'm looking at a metric far from Minkowski, because this is only used outside a compact region. So we are not looking at the black hole at all by doing this. Then the conclusion is that the corresponding initial value problem for the Einstein massive field equation admits a global hyperbolic Cauchy development, which is asymptotically flat, which will be easy because it will coincide with Schwarzschild outside some compact region, but of course this compact region is increasing as time goes on. And this spacetime will be shown to be future geodesically complete, which means that every affinely parametrized timelike geodesic can be extended indefinitely to the future. So that's the result that we expect. Right? You start with, you put some matter, the matter has some mass, so it does somehow modify the geometry. I mean, the modification, as you will see in the estimate, it has a real effect on dynamics. But since it is small, so I hope that smallness was was assumed, right? I wrote close to, I will be more specific in a minute, but we are really looking at a case where the matter is small, we are close to Minkowski, and the matter disperses. That's what we show. The matter just disperses in the future. Okay, but to do that, to prove that, a lot of work, and the first step is to express the Einstein massive field system in wave coordinates in this form. The box tilde is something we call the reduced wave operator. So it's not necessarily the wave operator because there is one term missing, but the term which is missing is actually 0 when the wave condition is imposed. Right? So you can think of it as being really the wave operator. So I put it here. So box of G alpha beta equal. You recognize quadratic terms in dg here, which we know already. And you also see the coupling terms here, d alpha phi plus v of phi. The Klein-Gordon equation is here. So the coupling is, I mean, there are two levels of coupling. The coupling is through the metric, the g here and the g here. So of course you cannot solve the Klein-Gordon equation independently. It's coupled to the metric. But also the equation for the metric itself contains quadratic interactions. So first derivative here and this phi squared. Okay. So this is a system we want to solve. So I will show you a little bit later that there is a decomposition of the quadratic terms where some of them are null terms in a usual sense, but there are other terms that are not null. So I have called them quasi-null terms. They were called weak null terms before, but I believe that quasi-null terms is more appropriate. We have the initial data set as I described before, which therefore coincide in a neighborhood of spacelike infinity with a spacelike slice of Schwarzschild space in wave coordinates. So I need now to be a little bit more concrete in order to formulate the problem, right? And so what I need to show you now is the expression of the Schwarzschild metric in wave coordinates. So here it is. So GS is a Schwarzschild metric, and I have coordinates tx here, and that's my expression for the Schwarzschild metric. So this is what we will take outside a compact region. Ms is a mass, is the ADM mass. R is a length of x. So x is in R3, right? X has 3 components. And omega A, so A goes from 1 to 3, is xa over R. Okay, so that's the expression that we are using for the Schwarzschild metric. Now we have the formulation. So we consider an initial data prescribed on the hypersurface t equals 2. For instance, I mean, it really doesn't matter. It's that I have normalized everything to be bigger than 1 because of the picture I showed you before. So why not taking 2? And the metric is known on this initial slice. Time derivative is known, phi is known, and dt phi is also imposed. Outside this ball, r bigger than 1, you have this expression. So it's static, so it's 0. This is what I put on the previous slice. And phi and dt phi is 0. There is no matter outside. Then this is a result at the level of coordinates. There exists constant epsilon 0 delta and a C1 and an integer, large integer. So n is the number of derivatives that we are taking from the initial data and the solution. So such that if you denote by h the difference between the curve metric and Minkowski metric, you have a control. This is an assumption, right? So you assume that your metric dh0 is controlled in hn and phi 0 and phi 1 are controlled in this way. The mass also is sufficiently small. That's what you expect, because if the mass is large, I mean, something completely different could of course occur. And the conclusion here is that the initial value problem for the Einstein massive field system admits a global in-time solution in wave coordinates, satisfying some energy bounds. And the energy bounds have this form. So the energy bounds, if you look at the metric, and you know, you get something which is of the order epsilon, but it could grow. So this is an L2 norm of derivatives of a certain form, right? The derivatives are not arbitrary, There are derivatives in D and L of a certain order, and they could grow like S to the delta. You have a similar bound here for the scalar field, the massive field, which also could grow like S delta, but this is only for n small. I mean, not so small, but not up to the highest level of differentiation. And then you have this middle line here, which says that the scalar field, if you want to look at high derivatives of the scalar field, then these high derivatives of the scalar field, actually they are not only like S delta, but they are S delta plus 1/2. So these are the bootstrap assumptions that we will make, and we will close that by showing that we can improve them. So the proof uses this hyperboloidal foliation, so killing fields that are the translation of the hyperbolic rotations. We use Lorentz invariant norm. We have to study commutators. To do the Einstein equations, you have to understand more deeply that what I have stated, the structure of the Einstein equations, especially the tensorial structure, which is behind. And there is an interesting interaction between the wave coordinate condition and the structure of the equation. So Lindblad-Roniensky discovered this structure here, quasi-null, so something I call quasi-null structure. They call it weak null structure. And an important aspect of the method is the derivation of sharp pointwise estimates. And these estimates will be obtained in various ways. So there are 3 or 4, I think there are even one more argument. We will use explicit integration along characteristic arrays. So the idea here is that there is a curve metric in the problem, even though you want to say you have Minkowski plus a perturbation, but the perturbation is not that small. So you have to take into account the metric and the curve metric, the perturbation to the metric. And this perturbation has some geometric global effect that you have to take into account. So if you want to get sharp estimates, you need to be very explicit and to integrate along certain characteristics or certain rays in the problem. You also need some estimates which we call L infinity estimates for both the wave equations and the Klein-Gordon equations. So these estimates tell you that if you have a subnorm control of the source in your equation or the initial data, then you have a subnorm control of your solution in some spaces. I mean, it's not direct, but it's an estimate in that spirit. And there is also this hierarchy of energy bounds that we have to introduce. So like I explained in a main result, but there are even more than that when you go through the proof, you have to introduce various levels of regularity and energy, and some of the quantities, some of this energy will grow slightly, some will grow a little bit faster. And very often we get some control, but which is not a sharp one, so we have somehow to iterate the arguments a couple of times in order to obtain the sharp result. I would like to finish, before the break, I would like to finish by showing you what I call the quasi-null structure of the Einstein massive field system. So let me state it, right? So look at the Ricci curvature, and the statement that I'm showing you here is a decomposition of the Ricci curvature, right? So the Ricci curvature, you remember it involves 2 derivatives of the metric. So the first term here is, and there is a summation, right? Lambda delta. There is a summation here. So this is exactly the box tilde operator that we have introduced, right? Modified or operator. So the Ricci curvature, you could say it's roughly like box of G alpha beta. Then there are 2 more terms. There is one term which is a differentiation of the Christoffel symbols, but if we impose a gauge condition, the Christoffel symbols will vanish. So this term will also be gone, but observe that all this first line contains terms with 2 derivatives of the metric. Okay. And then you have a big F alpha beta. So F alpha beta is the sum of 3 terms. First term is this, and these terms are null terms. So they have the same form that I showed before, like nabla U, nabla V, and with a summation that involves a metric. So if you look at each of them, they all have this structure. But when you compute, I mean, you may hope that that was only what you would get, but this is not true. So if you do the calculation, you get this, but you also get other terms, and if you look at them, they look similar, but unfortunately they don't have quite a null structure. So I suggest to call them quasi-null terms, and the way they will be controlled, so I guess I will have no time today to explain this, but the way they are controlled is by using the wave gauge condition. So they are not directly controlled, but if you look at the wave gauge conditions, they allow you to do some additional transformation here, and in the end to get yet a good control, like they would be null term. But they have an effect on the growth of the energy. So it's not, you could not just say that they disappear if you use a gauge condition. This is not true, but they can be controlled with a gauge condition. And there is one more term, and this term is like this. It's d of the metric gamma squared. So it contains a gamma again, and so it has the same feature as this. If you assume the gauge condition, this is gone, and this part also is completely gone. Okay? I will take a few minutes to tell you, first of all, to tell you some consequences, right? So look at this in the vacuum. So if you do it in a vacuum, you have box tilde of G alpha beta is P alpha beta plus Q alpha beta W plus this. So this is our identity. And so if I do impose the wave condition like this, all the gamma are vanishing. And therefore W and d gamma are gone. And you only need to look at this P alpha beta and Q alpha beta. If now you do the massive case, you have an equation like this for the Ricci curvature instead of 0, right? You have this additional contribution here, that's this coupling term, and therefore you get it here, right? You get this coupling term that comes from here, you get it here, and you need to keep track of the Klein-Gordon equation. The proof of the decomposition is quite involved. So I have a few slides here. So let me show the beginning, and then I will just leave you read the details. So you start with a formula for the Ricci curvature, right? Which is this line that you all know. You also have a formula for the gamma here, which is given by this. And what you want to do first, you want to look at second derivatives, right? So look at the first part here. It contains second derivative, right? According to the gamma is like dg, and so this part contains second order derivatives. And so what I'm doing here, I'm differentiating the Christoffel symbols once. So I get all these terms. So it's direct from here. You had 3 terms, and you get 3 terms here and 3 more terms here because you have differentiated the product. Then you do a summation here, which is different from the top, right? On the top here, I actually do a summation with respect to lambda. And here I do a summation with respect to, again, it's denoted by lambda, but this is inside the differentiation. So for some reason, I can shorten the expression. And therefore, what you are getting here is a second order term for the Ricci curvature. So you sum these two quantities here, and you get all these this long expression. Okay, so you could see that you have second order terms in a metric, of course, not surprisingly. But you also have products that involve first order terms. I mean, product of first order terms in the metrics that you have to also to understand. So you use this, right? You start with this, and you try to compute things step by step. So one way to conduct the calculation is to look at what you want to find, right? So what you want to find something which contains this term here, right? So there is a good term that is box of the metric, and you have this quantity here. So since you know what you want to find, why not computing this quantity? So that's what I'm doing here. I just compute these quantities. I want to consider this which appears in our decomposition. So Christoffel symbols are given by this line that we know. and I do the contraction with respect to one index to compute gamma, gamma, gamma. And I get this line, and I compute the derivative of that expression here. I mean, I told you that it's really technical, but I just want to give you the flavor of the calculation. So what I'm doing here, I have contracted the Christoffel symbols once, so I get this gamma lambda. I do a differentiation of this. So you have to compute all this product, you get all these terms. And by symmetrization, d alpha gamma beta, d beta gamma alpha, you get that, right? Just symmetrization of the line before. And now you look at what you have. So you know that this is something that you will keep somehow in your final formula. These terms are okay. So what I want to observe now is that the second order terms in this expression are exactly some terms that I just found before in the previous slides, right? So this is something I want to keep, and this is something that I was trying to compute, but in fact, you observe that some terms are the same. So that's good news, and you also observe that the last term in one quantity coincides with the last term in another quantity. So in the end of the day, you have a formula like this. So you have the part that contains two derivatives in the expression of the Ricci curvature, which you were able to express as the wave operator on G alpha beta, this term that we are happy to keep, and all the other terms. So there's still quite a few terms left, but the terms that are left are only terms like dg times dg, right? They are products of two first order derivatives. So that's a formula. You collect this a little bit more, and you even observe that two terms are equal. And yeah. So two terms are equal, and I guess to see that or to transform, I forget where it is exactly used, but there is an identity here that is also used. I mean, this comes from the fact that when you contract G with G, the indices upstairs, downstairs, you get a delta Kronecker symbol. So you can differentiate this relation, and you are able to move derivative with these indices upstairs to derivative with the metric with the indices downstairs. Okay. And I think this is what is used to show that the two underlined terms on the previous slides are cancelling. And this is our formula, right? So we are still not done because we have 1, 2, 3, 4, 5 terms. And so we continue in the same spirit. In the expression of the Ricci curvature, you had also quadratic terms, right? So you have to compute those. And that's what I do here. Gamma, gamma is given by this. I compute another quantity, gamma, gamma, with indices contracted differently. You put that together, and you get the quadratic contribution in the Ricci curvature. And you observe that there are, terms that I'm going to say something about them, but this is basically the additional contribution that you add to the Ricci curvature. And now you are getting closer to the end of the proof, because you now can look at the terms that you are left with, right? And you observe that some of these terms indeed have the structure that you want. So like the first 3 terms here are null terms, so that's good. The fourth term here is not, but this is a term that you are happy to keep as quasi-null term. So it has a different structure, but there is nothing else you can do but keep it. So you keep that, and now you are left with this last line, and you continue. 2 underlined terms will be opposite to 2 other underlined terms that I'm going to derive in the next slides. And the conclusion here is that only the last term here remain to be dealt with, right? So I have one term, essentially these two will be gone, but okay, it's only understood a little bit later. But from this slide, there is only one term left that we don't understand yet. And it comes from the quadratic gamma. And so this is a list, omega 1, omega 2, omega 3, 4, 5, 6. And these are the terms that I just introduced. And now you could hope that it is over. But it is not. And you have more and more of these good things, and the underlined terms here are cancelling with the previous slice, etc., etc. And if you want to go through that, okay. And I hope there is no misprint, but I believe there is no misprint in these pages, because I did that a couple of times, good number of times. Okay, so in the end, you collect all of that, and you get the identities that I mentioned before. So we make a break, and when we resume, I'm going to tell you very concretely about the proof for wave equations with null interactions, and then the sketch of the proof for the coupled system with strong metric interactions. There will be two sections here. I'm going to start with the simplest possible model, where you just look at a wave equation with some prescribed initial data. So you look at the Cauchy problem for the simplest model. And I want to explain the method with a number of details so you really can understand everything for this simple situation. And then we will move to a class of system with what I have called strong metric interactions. And with this class of model, we'll be rather close to understand the full Einstein system, but not fully, and there will be a couple of remarks in the end to tell you what are the additional ingredients that you also need to introduce. So keep this in mind. Box U is P alpha beta, D alpha U, D beta U. There is an initial data which I prescribe on one hypersurface, H S0, and the derivative also is prescribed. The standard null condition is assumed for the quadratic source, and the assumption will be stated in terms of the hyperboloidal energy for the Minkowski metric. In any case, that's the only metric that we have here. Only the flat metric is relevant in this problem. There is no Klein-Gordon term at all, even. And all the norms will be defined by using the space-time translations and by using the Lorentz boost. This is a result, global existence theory for wave equations with null interactions. This is an old problem that was covered with other vector field methods before. But here we revisit this problem in the following way. So we show that there exists an epsilon 0 positive, a C1 bigger than 1, such that if you give me some initial data satisfying this energy bound, so I have put here, I have first of all computed the energy on an initial hyperboloid, and I have introduced all the translation and boost by combination, so I can multiply them, compose them. And I do that up to an order which is 3. So the regularity of the solution will be H4, if you like, 4 derivatives that we control initially according to this norm. Then we show that the Cauchy problem admits a global in-time solution which satisfies a similar bound as this one, which now I'm stating on the foliation for every time s. So the statement is essentially the same here, the initial time and an arbitrary time s. And of course, you have increased from an epsilon size for the initial energy. You now have moved to C1 times epsilon, where C1 is some constant bigger than 1. And there is also an estimate for the decay of U, which is D alpha U, which is controlled by, roughly speaking, it's like 1 over T. At least if you are close to the light cone, this is exactly what this estimate is telling you. Okay? And there is also always some epsilon in front of that, so all the energy quantities that we are talking about will remain small. The bootstrap strategy is stated in the following way. If you give me some sufficiently large constant C1, I can set the bootstrap assumption in the following way. So I take the energies that I had in a theorem, which less or equal to C1 epsilon, and I'm writing the estimate that I want to obtain on an interval of hyperboloidal time, which this interval I call it S0, S1. S1 is defined, is chosen to be the largest hyperboloidal time such that this inequality is true. That's the one that you want to prove, right? So it just takes a largest S1, satisfying this inequality. The first remark you have to make is that S1 is strictly bigger than S0, and this comes from the local existence theory and the fact that you have continuous dependence for local in time solutions. So for a small time, the energy that was less than epsilon cannot exceed C1 epsilon if C1 is strictly bigger than 1. So you do have a way to initiate this process, and what you want to show by contradiction is that if S1 would be finite, if the solution would be only defined on a compact interval, that's what you can prove now. You are going to prove that at least if this constant epsilon 0 C1 are chosen properly, this energy bound implies something much stronger, which is C1 over 2 times epsilon. Right? So you start with some inequality, and you show that it is true strictly with a much smaller constant. And so if this is the case, so it's clear that S1 cannot be the largest time. You get a contradiction unless, of course, you have a solution defined for all times. So that's what I want to do here, and I will really give you all the details, right? So everything I'm saying here is more or less complete. I mean, there are things that you still would need to check. So I even summarize again our statement. So let U be a solution defined on a compact interval with an initial data less than epsilon. In this sense, this energy, weighted energy on the initial hyperboloid being less than epsilon. Then I want to show that there exists epsilon 0 C1 such that if the energy is less than C1 epsilon for S in this interval, then in fact there is a stronger estimate, which is the same with C1 replaced by C1 over 2. Let me recall our notation. The semi-hyperboloidal frame consists of 3 vectors tangent to the hyperboloids. I wrote them on the blackboard. So d bar A is LA over T equal to that. So we take this as a part of our frame, and we supplement this frame by dt, which we call d bar 0 also. The set of vector fields that we use to differentiate the equation is d alpha and LA, translation and boost. And therefore we work with that. So the first step is to derive an energy estimate for the hyperboloids, which is this statement here. So the energy at time S is bounded by the energy at time S0 plus the quadratic terms. So here I have taken the quadratic nonlinearity, P alpha beta, D alpha U, D beta U. I have applied Z, actually several of them, up to 3 of them, and compute the norm, the L2 norm of that, and integrate it. Right? So this is basic energy estimate. There is nothing new here, but I still want to show with a few lines the calculation. And the first remark I want to make is that the L2 norm, which I'm using here for convenience, is not really the L2 norm which would be intrinsic to the hyperboloids, because there will be an additional weight that I don't want to carry over in every estimate. So I defined the L2F refer to flat, if you like. So L2F of HS is simply defined by using the dx element of integration. So in other words, what you do here, you take a function u and you do this. Right? You integrate with respect to x, you put an x here, and the first component is s squared plus norm of x squared with a square root. To derive this energy estimate, nothing surprising. You use a product Zi with the length of I being less than or equal to 3. You use a commutation property that tells you that Zi commute with a box operator of Minkowski space. So you can do this. You can just move Zi inside and apply it to the source term. Now you do the usual energy calculation. You multiply by the time derivative of ZIU, which I'm calling U tilde for a second here. This quantity satisfies an energy energy identity, right? So here you recognize dt U tilde square plus the norm of the spatial derivatives. You have a flux contribution which takes this form. And you have the source, and the source is simply the source that you had before, differentiated with Zi and multiplied by dt of U tilde. Next step is to integrate between two hyperboloids, the region, shaded region that I showed you before. And if you take this and you integrate, you simply, so at this moment I didn't do much, I just put an integral of k s0s in front of these terms, and I have to integrate in space and time within these two hyperboloids. On the left-hand side, you apply the Stokes formula to transform the quantity, because it's at the divergent form, so you can transform it to a flux on the top and a flux on the initial hyperboloid. There is no contribution from the boundary, as I explained before. And the notation here is that n is a future-oriented unit normal to the hyperboloids. This sigma is the induced measure on the hyperboloids, right? So this is a measure that I don't really want to use throughout the proof. I prefer to use the dx. But of course, here I'm taking care of that weight. So you get two fluxes, and what I did here is just to compute the dot product here, right? This is a vector. There is a vector here in space-time. You compute this dot product, and you obtain this, right? So this is a flux on the hyperboloid HS, and here you have the flux on the hyperboloid HS0. Of course, this is not, it's not clear that this would even be, definite, right? So you transform this a little bit, and by an easy calculation, you realize, with no surprise, of course, that this is the hyperboloidal energies that I have introduced before. So you have found the energy minus the energy at the initial slice, and the energy was defined before in this way. So remember that this time derivative is multiplied by a good factor. Here you have a special derivative, you have a Klein-Gordon term, but here I'm only doing the wave equation, so you just forget about this C, and EM is just the usual energy of the wave equation. So far so good. And then you look at the right-hand side of your identity. You have S prime over T dtu Zi of the quadratic term, right? So just change of variable allows you to, instead of having a space-time integral, you can first integrate, you integrate with respect to the hyperboloidal time, and you integrate on each hyperboloid. So that's just a formula. And consequently, that's what you have found, right? So we continue by now, it's convenient to differentiate with respect to S. So you get E dds of E, and it's convenient to put a 1/2 and then a 1/2 in this way. The 1/2 is gone in this calculation. And on the other side, you find the quadratic source, which is somehow average on the hyperboloid. And this is a place where you hope that things will go well, right? So you control this guy here as an L2 integral with a flat measure, with a dx, and you keep the rest, right? And the rest is a quantity like this. S over T dtu in L2 of this hyperboloid. And it's going to work because you observe that in the hyperboloidal energy, you precisely had this term, right? With this weight. Exactly this term was written in the definition of E. And there was other terms, but I don't care. And therefore, you can replace this by an energy E of SU, and you divide by it, etc. And you sum. So this is something that I have done for every Z, I. Now I sum over all possible Z, over all possible order of differentiation. And you get dds of this sum is bounded by the sum of this source term. Okay? That's what we wanted. If I translate this result, right? So this result is a good bound on the energy, on hyperboloid. So if I transform this in terms of derivatives, this is what I've obtained. So again, you remember that in front of dt, there was an S over T. This is computed in the L2 norm. And d bar A had no weight. And therefore, this is exactly what I have obtained by expressing the statement of the L2 estimate, the energy estimate corresponding to the hyperboloids. Right? So that's what we have, given by our bootstrap argument, if you like. Now you can now commute. What I'm doing next is that I'm commuting Z and D bar A. So there are a lot of commutators that come in a picture. So you have to compute all of these and realize that they are nicely bounded so that you can actually move the Z or part of the ZI. You have here ZI1, ZI2. You can move that any way you want and you keep the same bound. Maybe not the same constant, right? So the C means some constant that may change at each occurrence. To prove that, you need the so-called commutator estimates, which are written here. So you want to commute Zi and D bar alpha or D bar A and so on and so forth. And at some point later on, we would also need to commute with two derivatives in this way. So at this moment, we are not using those, but we are using typically this line. And so this line tells you that when you do this commutator, you get terms that are nicer, if you like. Right? So when you do the summation, things fit well. So we have the energy bound, we have the energy by having commuted the Z in this way, and then we continue. So the next step is a Sobolev inequality, which now we have to express on hyperboloids. So that's the statement. The statement for hyperboloids is that so essentially you want an L infinity bound by using an L2 or L2 bound or H1 or H2 bound. So that's what I'm doing here. So I'm saying that the subnorm of U is bounded by two derivatives. I mean, I put I bigger than less or equal to 2 of U. And the point for this, first of all, there is a weight, T to the 3/2. And second, all the derivatives that come here are only derivatives that are tangential to the hyperboloids, right? Which is, of course, is expected because this is a statement that you make on one hyperboloid. Right? So that's what you expect. But still, you have to prove it, check that, and make sure that the weight here is correct. So that's one ingredient. And if now you combine this statement with the energy bound that I just discussed, you get this result, right? So I'm going now to apply that with the derivative, right? And so if you do that, that's what you get. So you see that this power T3/2 comes here, and here there was some simplification because you had a T or some cancellation. If you like, you have a S over T in front of the time derivative, and so this 1 over T has cancelled part of the T3/2 that you had upstairs here. So I have now a subnorm bound, but the subnorm bound here you can see that you have to drop, you had a 2 here to control the L infinity norm, and so here we started with a 3 and now we have only a 1 here, right? So this statement, the subnorm control is only valid up to for Zj, but J has to be of length at most 1. Okay, now we already have part of the work done, and now we would like to understand the quadratic terms, right, the null forms. We decompose the null forms on our frame in the following way. So dtu square, I mean this is an example, and then I will show you a general lemma, but this is an example. If I take dtu square minus the sum of dau square, and if I use our frame, right, d bar 0, d bar a, so a little bit of calculation will give you this. And I want now to control that, right? The null form, we want to control some L2 norm of this null form. So to control this, you need to control all of these terms. And that's what this lemma is telling you. If I have a null quadratic form, I have a calculation like this, so an analog. Now I have U and V. And instead of computing just that, I also put differentiation Zi on top of this. And that's what I get, right? So look at the terms. You have terms here which are either product d bar A and d bar beta. So A goes from 1 to 3, beta goes from 0 to 3. This is an analog with just different, U and V and V and U. And so these are somehow good terms, right? So d bar A are good, and here for each of them, each of these two products contains a derivative, a tangential derivative to the hyperboloids, d bar A. Now you have one term which is possibly bad. So here's, this derivative ends up better L infinity L2 decay. So these are good terms. And the derivative in time, which we see here, we have product of two of these, right? Is actually, in principle, it is bad, not enough decay. But there is a good factor, which is this term here. S over T is good. And this is something you can remember the inequalities that I wrote before, that T was between S and S squared, basically. So this is a good term, and all the proof is based on, one important ingredient is to understand how to use this good weight. We can now obtain a good estimate for the interaction term, and this is the estimate. So I'm going to compute Zi, P alpha beta, D alpha U, D beta U in L2 norm for the flat metric on the hyperboloid. And this is what I'm going to get, S to the power 3/2. C is a universal constant, it's just a number. And C1 is the same C1 that we had in the bootstrap argument. And the proof for that, of course, you return to the identity we just observed for null forms. So null forms contain such products or contain products of time derivatives, but with this good factor S over T. And what I want to do, I want to control that. And to control that, I'm going to combine. We have two things that we have done already, L2, an L2 bound, and an L infinity bound. Right? So we have to use both. And we do it like this. You look at the terms in T1. There is a summation that you have to do for two indices, I1, I2, bigger, less than 3. But of course, if you have the sum of two numbers less than 3, one of them should be at most 1. So I'm using that. I assume that it is I2, which is less than 1. And I do this. So first, I take the product of the two time derivatives, dtu with this good factor. And what I'm doing here, I put S over T times this in L2 norm, because we know that this is good, right? S over T is the right weight that you have to put in front of dtu, and there is an energy, and we have that even when this index I1 is big, but here I2 is small, somehow, I2 is less or equal to 1, so I2 is small, and for small order of differentiation, we have a subnorm bound. And the subnorm bound, if you look at the previous page, you will see that it's T1/2 S, because it was really T3/2 S over T that we had. So this is good in subnorm, and you are left with a T, but the T can be controlled by S in this way, S minus 3/2. Okay? Now, if you have understood that, you have already understood everything, because the idea for now a product d bar A of U, d bar beta of U, I will do two cases. If I1 over here, if this I1 is small, I put a subnorm on that, and L2 norm on Z I2. And I get again the S minus 3/2, so all the weights, fit properly. And if this is I2, which is small, then I will use a subnorm of the quantity containing I2, and I will put the L2 norm of the quantity containing I1. And again, I will produce the same S power to the 3/2. Okay? So this is the end. The energy on one hypersurface, one hyperboloid, is less than the initial value of the energy plus the integral of the source, a quadratic source. But we just show that the quadratic source was S to the power 3/2. And if you integrate this, you get something finite. I mean, there is a uniform bound for this quantity. It's integrable. And you see that it's of the form epsilon for the first part. But then what you are adding here is epsilon square times this constant, C1 epsilon square. So you look at what you have obtained, and you insist on this being less than C1 over 2 times epsilon. That's what you want for the bootstrap. And that's indeed possible if C1 is bigger than 2 and if epsilon is small enough. Okay? So you really, I mean, you have the whole proof, except maybe the commutators. I didn't show you the commutators, but it's just a rather simple calculation. Now, this is only the very, the simplest model you can think of. So the second class of model we have studied is a class with weak metric interaction in a sense that I explained before. And now let's move to the so-called strong metric interaction case. That's what I'm doing now. I take box U equals quadratic terms, but now involving V, right? This is quadratic in terms of the Klein-Gordon component. There is also quadratic terms V squared coming from the Klein-Gordon component. And on the Klein-Gordon equation, what's important, what's new, is this strong metric coupling where I take the wave term, U, the wave component, and I use it to somehow modify the metric in the Klein-Gordon equation. So the relevant metric for the first equation is a flat metric, but the relevant one for the second equation is a modification of the flat metric, and the modification involves U, involves a product, but U doesn't decay very fast. Right? So that's a most delicate term. We don't need to assume any null condition here. So these are really arbitrary. The theorem that is proven here is a global existence theory for wave Klein-Gordon system with strong metric interactions. So we take such a system. We take an order of differentiation now, which is something bigger. And we can show that there exists an epsilon positive, such that if the initial data in Hn plus 1 or Hn are less than epsilon, then the Cauchy problem for this model problem admits a global in-time solution. But now there are much more terms, much more difficulty. So first way to see it is in the bootstrap assumptions, right? So if you remember the bootstrap assumptions I show you, you can compare with this. And so here we have a scale which is like that. And so let me make some comments about this. The wave component is this variable U. So if you look at the higher order energy, I would say it's quasi-conserved, meaning that in this line here for the large number ij, you have a bound, but it's not, it can grow, but it grows like s to the power k delta. So k is the length of j, it's a number of L that you take to differentiate your solution. So you have some mild growth here, but delta can be taken to be as small as you want, right? So it's algebraic, it grows, but in fact very slowly. You have now the low order energy is conserved, so that's the statement which is here. You have a uniform bound for that, but it's only when I plus j is less than n minus 4. And now you have two more properties here, two more bounds for the Klein-Gordon component V. If you look at the low order energy, right, which means low order energy is this line here, I guess, no, it's this line here, you have again a growing quantity here, but it grows very slowly. Delta can be taken as small as you want. So this is very slow. And so there is only one case where you have real growth, which is for the high order energy of the Klein-Gordon equation. Right, which is this line, this S1/2 plus some small quantity. And this happens to be specific to the strong metric interactions. The proof is using the natural metrics which are behind. So for the first equation, the natural metric is a Minkowski metric, but for the second equation, as I said, if I go back here, there is really a metric here which is different, right, which is Minkowski plus U, H alpha beta, D alpha, D beta. This is a matrix that you have to work with, and you do the energy estimates by using this metric. Okay, so we proceed with along similar lines, but many more ingredients on top of what I already explained. In particular, the RD inequality, a variant of the RD inequality must be used, and some technical lemma, which are L infinity lemma for wave and Klein-Gordon equations. Let me start with the RD estimate. If I have, actually there are two statements. One statement is on a given hyperboloid, and the statement that you see on the screen is more or less what you would expect, right? You take U over R in the L2 norm, and you control that by the derivative, by one derivative. Right? But of course, the derivative is taken on the hyperboloid, because that's really a statement that you can write intrinsically on a given hyperboloid. And there is a second statement where now I want to move from one hyperboloid to another and look at the whole foliation. And I do U over S in some hyperboloid in the future, bounded by U over S0 in the initial hyperboloid, and then there are contributions that come. So one term which is similar to the one on the top, but there is also an integration along the foliation. And of course, this is deduced from the one on the top. And the one on the top is proven by introducing a vector field, which is a bit complicated, but if I tell you the analogy with classical RD inequality, you will understand. So it's really like it's really like 1 over R times U squared. There is a cutoff function here related to the light cone, but roughly speaking, what we are using here is like U squared over R, and in fact, there is really a nice proof that you can do for the classical RD inequality by doing this. So you compute the divergence of U squared over R. But the divergence that I have in mind here is taking 0 for the first component. So it really means that I'm only differentiating with respect to R. Right? So dr U squared over R, just integrate this quantity with a divergence Stokes formula, and you will get a nice proof of RD's inequality. So this is an analog. I mean, this is a complete analog. What I wrote below is, if you like, I mean, this is a very simplest case, a 1D proof of RD's inequality, if you like. Okay. But this is more complicated. XA is a component, right? These are the components in X, right? So A goes, this is T times XA, A goes from 1 to 3. Okay? So this is why, X, so you have TXA, so it's really like XA over R squared. Of course, this is not exactly the same, right? But by analogy, this is, very similar to doing U squared over R, because the dimension here is similar to 1R on the top and R squared on the bottom, right? So this is really the same dimension. So I'm now stating, a few technical lemmas that we will need, and in the end, I will try to collect all of that to tell you how we complete the argument. So the second statement is L infinity bound for the Klein-Gordon equations, and we start with this, right? So we now look at a curve metric. So box tilde G of V plus C square V is equal to some source term, some F. The matrix that we have in mind here is a perturbation of the Minkowski metric. So H is a perturbation from Minkowski. One of the components is, this component here is assumed to be small. Okay, this is a component in the hyperboloidal frame. It's not a restriction because H is small anyway, so that's something quite reasonable. And what I'm going to do now, I'm going to look at not V directly, but I'm going to scale V by this quantity lambda 3 half, and I'm going to look at V along a line. So I fix Tx, and I look at lambda. If lambda is 0, I am at the center, 0, 0. And when lambda is S, I start from some point, Tx. Right? So I have a line connecting Tx to the origin. I look at this function for a fixed Tx, and I express the wave equation on a curved background. Right? This is not a wave, but the Klein-Gordon equation on a curved background. I express it by only looking at the time derivative, basically. I mean, not the time derivative, but the derivative in this variable lambda. Okay? So it's like a time derivative, but on a line which has been defined through this variable. And this is what you get, right? So you get a second derivative in lambda of w, v scaled in this way. Then you will get a source term which contains a lot of terms involving special derivatives, and I will show you the expression, but this is not important. So the key point is that you want to, of course, to keep the second time derivative from the box, but you also want to keep the effect of the Klein-Gordon. Okay? So the c square w that comes from c square v is kept. And when you do the calculation, there is this component of the metric 1 plus h bar 0, 0, which is essentially the component of the metric in the frame that we are using, right? So we had basically, this was a coefficient in front of this derivative, and we have divided, and we get c squared over 1 plus h bar 0. So this is variable. It's small. It's supposed to be, say, less than 1/2, so this will never vanish. And you have now an ODE. On all these lines, you can write an ODE, and you need to analyze, right? You want to analyze that. So the analysis is done by using hyperboloidal coordinates, so which are the same coordinates I was using so far, xa on each hyperboloid, but in addition I supplement that not with a t but with an s. Right? So these are coordinates that are quite natural to use. H bar alpha beta are the components in my hyperboloidal frame. And the hyperboloidal frame, if I want to repeat, it is d bar, you know, the d bar xa, which was already defined in this way. And the only thing that I'm changing, instead of dt, I'm now working with ds, which is s over t times dt. Okay? Now you may want, or maybe you don't want to see the expression of this k, but still I will show it to you. So there is a complicated expression here that contains, you know, space derivatives essentially that come from this guy, right? The operator. I keep the time, I keep the Klein-Gordon effect, and I put all the rest in this k. Okay. So of course the k is going to be an ugly expression. I write it like this: r1 plus r2 plus r3. Plus the source that I already had in my Klein-Gordon equation. And the expression is this. Okay, so it doesn't matter. I mean, the point is that these are good terms in some sense. What I have done, I'm looking at the bad term of the equation and understanding the effect of the Klein-Gordon contribution to the dynamics of the Klein-Gordon equation. So these turns out they will be good terms. And now we proceed by using a technical ODE lemma that tells you that if you have an ODE like this with a source, there is a way to get a nice control. So I fix a function g and a function k. Both of them are integrable, or g prime and k are integrable. And I look at an equation like this, exactly the equation that I wrote, right? Z, two derivatives in lambda plus c squared 1 plus g of lambda, z of lambda is equal to some source term. And what you want to do, you want to get a good subnorm bound on z by simply integrating this second order ODE. Okay, so it's not difficult, but you have to do it carefully and make sure you get the correct quantities here. So the bounds that we are getting is a bound for the subnorm of z, so the amplitude of z, and its derivative by the initial data, by k is a source that we had here, so it's given by all this stuff here. So this is the part that you would have expected. But then there is another contribution here, and the contribution is what you want to understand. You want to understand what is the effect of the geometry. If g was 0, you know, this would not exist, right? There would be no contribution. So this will be easy if you have a Klein-Gordon, I mean a second order equation with a constant coefficient. Everything can be explicitly done, and the intuition behind it is clear. But here you have to take this into account, right? So you are really understanding with that, you are really understanding the curved geometry at the level of the Klein-Gordon equation. What is the effect of the Klein-Gordon, the good Klein-Gordon term on the curved geometry for these time derivatives. Right? So that's what is done here. So you do that carefully, and you realize that what you get is just a derivative of this guy. So if g is 0, no contribution, and then you have an exponential and the integral of g prime. And again, this would disappear when g prime is 0. So that's, you could say, just a technical lemma. But now if you plug that in a previous equation that we had for the Klein-Gordon equation, you get what you want. So I look at the Klein-Gordon equation, a curved background. I assume that the metric is a perturbation of Minkowski. I impose data on h0. And in the future of h0, this is what I get. So s3½ times v, t s1½ times this perpendicular derivative. So this is very much related to the scaling vector field, which I wanted to avoid. So it comes here, but as a result of this calculation. It has not been used really in the analysis. And all these weights are presumably sharp. And this is what you want, right? You get a subnorm bound of your solution of the Klein-Gordon equation by V, and the V is defined below, and the V is essentially the collection of what you have seen in a previous slices. So, let me, I don't think this will show much, maybe just to say that when you compute the derivative with respect to lambda, you actually get this orthogonal derivative like this. Right? So of course there is a connection, a deep connection between this derivative that you also want to control and the choice that you have made to parameterize your lines. Okay, so I mean I don't think you need to look too carefully at that. So the R1, R2, R3, that's what we had before, the source. And so this is F, and this F you put it on still. I mean, this was our source, right? And this source is something that you have to input in the lemma, right? And in the lemma, you remember that we had some integral and some exponential, blah, blah, blah. So that's what is done here. And all of these terms are good. I mean, they have better decay, so that's really the proper way to look at that. There is one more ingredient, which is an L-infinity estimate for the wave equation with source. So if U is especially compacted in the solution of the wave equation defined in our cone of interest, we can assume vanishing initial data because in the proof we'll do a decomposition and analyze the effect of the source and the initial data separately. So here I'm writing a lemma for the source. And if the source has a certain decay in subnorm with certain condition on the exponent, then you deduce that t times u, which is a proper scaling somehow, is also controlled with a decay that is related to the assumption that you make on the source f. And the proof is a little bit technical, but it's not difficult. It's based on the solution formula for the wave equation. So this is really a statement. It's much simpler in a way, at least conceptually, from the previous analysis for Klein-Gordon. So now what I would like to do next is collect all of that and tells you what sort of estimate, I mean, how we control various terms. So the proof starts like before. That is, we write energy estimates, and the energy estimates suggest some bootstrap as assumptions. And we start by expressing the bootstrap assumptions on this energy in terms of L2 norms. Right? So here, I mean, it's a little bit more complicated than before, but the spirit is really the same, that you have certain weighted norms, L2 norm, for some number of derivatives which are controlled. And the control is either, like I explained in the bootstrap condition, either sk delta, where k is the length of j, or if you look at Klein-Gordon components, they actually contain an additional S1½ as a growing factor in the estimates. So that's the starting point. You commute d alpha with d I L j, like I did here, and because the commutators can be nicely controlled, you get essentially, or even here, you get exactly the same estimates for these terms. Right? And there are more terms here, similar, on which you do a similar treatment. Now, you continue by applying the Sobolev inequality on each hyperboloid. And by doing that, you go from an L2 bound to an L infinity bound. Right? So it's really, you can see it directly. It's not so direct. There is some loss here that you have to keep track of, which is due to the commutators. So the commutators introduce a bit of loss here, but it's not a problem. And again, you do some additional commuting here, and you can control any combination of these derivatives in subnorm, right? So energy in L2 norm, commutators, you get L2 norms, you apply Sobolev on hyperboloids, you get subnorm bounds, and you do some additional commutation here, and you get another subnorm bound. Right? And of course here you started with some order differentiation, and by applying the Sobolev inequality you went from n to n minus 2. Now, before we could finish the proof with this, right, essentially. But now we have additional terms, interaction terms. So we need sharper bounds, and the sharper bounds are obtained with the ideas that I explained before, right? Number of lemmas that you have to combine together. And to give you the sketch, first of all, I state the results. So there is a subnorm bound for T Lj of u. There is a bound T3½ of this guy, and a bound T3½ of this orthogonal perpendicular derivative times the same quantity here, right? So you can really recognize, I mean, these two quantities, you can recognize this quantity was a quantity that arises already in a lemma, right? In the L infinity stability result for Klein-Gordon. So the proof of that is a little bit involved because it goes step by step. So you first apply the L infinity estimate for the wave component for u, and you get some result. And you do that for low order differentiations, less than some number n minus 7. And then you continue by deriving together at the same time another control for the wave equation, the Klein-Gordon equation, but this time at 0 order. So there is no differentiation, but I'm getting here something which is slightly stronger than that because there is no sk delta. And this is essentially the same as that, but without differentiation. And so to do that, you have to look at this lemma, right? So in the lemma, I insisted that there was some integral of g prime that should be appears, right? So it should be finite. It should be uniformly controlled. So there is a condition of uniform integrability of the coefficients of the ODE that have to be checked and held. And then you continue. Now you apply DI. You use the L infinity bound again, and another range of exponents, and you get that. Okay, so this is a sketch of what you have to do, but you apply this lemma a couple of times, and step by step you improve the estimates. Okay, so now in the next few slides, I'm going to put all of that in together, right? So I have nice energy bound and subnorm bound, and then in addition I have sharp subnorm bounds. What I need to do to complete the proof, I need to return to the basic calculation where you differentiate the system of equation by using DILJ, I plus j less than n. J is, k is a notation for the length of j. And you use commutation here, so you put the derivative inside, and you just write what you had, right? This was the quadratic terms, the two quadratic terms in the first equation. And here you have a commutator, because the H alpha beta that does not commute, so you have to keep track of a commutator. And here you recognize a Klein-Gordon structure. Right? So what you want to do energy estimate on this, and the energy estimate is controlled. The energy is controlled if you control the L2 norm of that on hyperboloids, and you get a nice decay in time. So that's what we do now. We want to control these nonlinear terms for arbitrary P alpha beta, H alpha beta, and R, and we investigate the decay in S, and we have three terms. The first term is this guy here in L2 norm for the flat metric. Second term is this guy, L2F of HS. And the third term is a commutator that comes from the last second equation here. Okay. So we have three terms. We could expect that this would be the most difficult term. And that's indeed the case. So we start with low order derivative. So if I plus j is less than n minus 4, you can check that we have more decay available here, and we can control directly the first two terms from the bootstrap assumption. That is our energy estimate and the Sobolev inequality on hyperboloids that we deduce. Right? So this is an easy part, low order derivatives of these two guys here. Then you have, and this is what you get. You get S 3½ plus some loss. Then you look at high order derivatives of these two terms here, and you cannot, it doesn't work. Right? You just try to do the same sort of calculation I did for the model, and it doesn't work directly, meaning that the basic decay rate is not sufficient, and we need to use a sharp pointwise estimate that I already stated previously. And then you have the third term, which is the most tricky term. And in this case, for any I and j, you can never control it. And here you need to use a sharp pointwise estimates for any I and any j. The sharp L infinity estimates have allowed us to improve the basic pointwise bounds as I show it. So this is a rewriting of the statement. So we have subnorm bound, a rather sharp bound when I plus j is less than n minus 4. And we proceed by looking at the control of P alpha beta and R, these two terms. We begin by the regime where I plus j less than n. I mean, this is the general situation. And we assume in this sum, so that's what I'm doing here. I'm taking the product, right? You can get rid of P alpha beta. I just look at any product like that. This P alpha beta is irrelevant. So you look at each term separately. And di lambda j of this guy in L2 norm is roughly like that. So you put di1 L j1 or di2 L j2 in this way. And then you look for a good control. So you do something similar as before, but now because you have sharp bounds, you are in a better situation to do the nice, to get a nice control. And so this product in the L2 norm, you take I1 J1 in a subnorm. That's what I'm doing here. And when you do that, you remember that our bounds, I mean, you can see the bounds on the top here. So these bounds, it's exactly written here. It introduced some loss, some power of S. But the power of S is like this, k times delta. But k is what? K is the length, is the number of L that you are using. Right? And so in this step here, what I have to put here is not really this k, it's a length, it's a number of L that I am using here to do the L infinity estimate. So this is really S J1 of delta, and the other guy is bounded in L2. And when you collect now these two, what you will see, you will get another loss of the length of J2, and the sum J1 plus J2 is exactly the length of J, right? So you do get K times delta as you wanted, and there is another S1/2 that comes in this calculation here. Now you can do this similarly. So for any any value, any order of differentiation, you can also control the other term. Okay, so the end of that. So I have used a sharp bound to control high order terms, And I can now conclude that I have the control that I wanted, because this is what you wanted. When you will integrate that, you will get exactly the increase of s to the power k delta that I have stated in the energy bounds, in the bootstrap assumption. So we are done with the wave component. That's treat the wave component because these quantities appear only, I mean, on the wave equation, you only had these terms. And now I continue, and now I need to discuss the commutator which were arising in the Klein-Gordon equation. And that's what you do now. You observe that if you look more, if you look at this commutator, you see that there will be a differentiation dILJ that should hit U, but it can be of low order. I mean, so there are classification here that is made depending on how many L J1, how big is this J1 in the scale which is here. So you look at, you decompose this in this fashion here, and you realize that the terms that are in the first class are controlled by more or less the same calculation that I show, and the terms in the second class here are more tricky because they contain an Lj of U, and we need to use the sharp decay estimate. So we had the statement for Lj of U, but in addition, we need to use the RD inequality for this. Right? So there is a final step here where the RD inequality, in addition to the sharp decay estimate that I showed before, will be needed. And let me show that. You look first at higher order derivatives, and you control this product. I mean, it's the same sort of idea, but you have to keep track very carefully of the weights. And so the point here is that in this regime here, the RD inequality for this guy is necessary. And this is really the part where the growing mode s to the power -1/2, but when you integrate, this will become s to the power 1/2. So it will produce the growing terms that I mentioned before. And if now you look at lower order derivatives, this is easier. And in this case, you get a bound which is like almost preserved, s to the power k delta after integration. Okay, so I've covered essentially what I wanted, and I will finish with only 2 slices. Now I still want to show you. If you want to deal with the Einstein equations, which is what was done is done in this paper, there is a number of additional ideas that I could not discuss today. First of all, the wave gauge condition is used to express the equation, and it gives you some good control. It gives you some good combination of the Christoffel symbols that are vanishing if you sum them properly, and so you have some information about certain components of the metric, first order derivative of the metric. So when you use that, the quasi-null terms that I mentioned before can be controlled, but this is at the price of a much involved algebraic structure. There is a hierarchy of low order, high order energy bounds, which also are motivated by this, which must be introduced. And there is an additional ingredient of integration along characteristics, which is also used. And a difficulty, I mean, a technical difficulty is that we cannot work with compact solutions, right? Everything I discussed in the technical part was for compact solutions. But if you want to treat the Einstein equations as we understand, you cannot assume that you have Minkowski outside the compact set. So you have the Schwarzschild metric outside the compact set. And therefore, you have to pay attention to various boundary terms that come in the estimates. Two more remarks here. The theorem that I have presented establishes that there exist no unstable solutions, no dynamically unstable solutions to the Einstein equations for self-gravitating massive fields, at least when the mass of the spacetime and therefore of the field, if the mass is sufficiently small. But on the other hand, if the mass is large, we know that bad things can occur. So that's, of course, a very reasonable assumption. I already mentioned that the technique applies to prove the stability of Minkowski space for modified gravity. Again, there are some smallness conditions, so you must be close enough to Minkowski space-time, and you have this theory where additional terms will occur. In fact, if you remember in the first lecture, I show you the structure of that, and in the very beginning, it is a fourth-order system instead of second-order system. So you have to understand the structure. That's something we have done. And I will finish with 4 open problems, and you are welcome to contribute. So the first problem is to apply this technique to cover a larger class of wave-Klein-Gordon system with this quasi-null coupling. So we have done that for the Einstein equations, using the structure of the Einstein equation coming from the wave gauge. But there were papers especially by Alinac, and I think Hans Lindblad also has contributed to that. But by Alinac, I saw that, where Alinac was able to define a class of wave equation, and in our case, it would be a Klein-Gordon wave equation. So look at a class like this, and you allow some coupling which do not satisfy the null condition. Okay? But they satisfy this quasi-null condition that you have to define for a general class, and that's what he did. So it would be, I think it would be very interesting to look at what he did and somehow extend his result by using this hyperboloidal foliation method. The second problem is to understand this growing rate, S1/2, that we are getting. So I don't know if this is part of the technique or if this is something deeper. Right? So you may want to investigate whether this growing mode here is necessary in a wave gauge, because that's what we have done, maybe by constructing some explicit examples. And the reason why this could be relevant, I mean, could really be a physical effect, is that by doing the strong metric interaction situation, you are really modifying the metric in a strong way. Right? This U, H, alpha, beta, etc. This is a genuine modification of the underlying metric. So maybe that's indeed accumulate and produce that. But at this moment, I don't have explicit examples to show that. On the other hand, it could also be possible that by adding some additional geometric argument and, for instance, constructing the hyperboloidal foliation from the curve metric, that by doing this, you could improve this rate, right? And maybe show that it does not occur. This I don't know. There is an ongoing work by Kian Wang, and Wang may be relevant to answer this question. The third problem is the extension of this method to other massive fields. So you can look at kinetic models where you have a density function in addition. Instead of a scalar field, there is a density function, depends on a velocity variable. So it's more involved. But I mean, it's simpler by some way and more complicated by some other ways. And you can look at the Vlasov. Already the Vlasov equation is already hard enough, but the Boltzmann equation could also be looked at and show global existence of Minkowski space for instance, the Vlasov equation, Einstein-Vlasov, using the method I presented here. In this direction, there are ideas that may be connected to that in this paper I already mentioned earlier. And the last problem could be to establish the Penrose peeling estimates. So these estimates are estimates that give you precise asymptotics on the space-time curvature along time-like directions. They were obtained by Christodoulou and Kleinerman in their pioneering work by using geometric methods. So the philosophy is that you have a frame that is very much tied to the geometry, but of course it's much more work to actually construct such a frame. But this was, I mean, this was in a work of Christodoulou-Kleinerman, understanding how the curvature is asymptotically approaching zero in a time-like direction. And at this moment, so far, we have not been able to prove these peeling estimates using wave coordinates. Right? So I hope I convince you that a proof using wave coordinates, even though it has to involve a number of arguments, it's definitely simpler than a proof which would be fully geometric. So at this moment, there is the peeling estimates have not been obtained, but I want to conclude by saying that it's conceivable that it could be done with this hyperboloidal foliation method, because the method provides sharp bounds. And for instance, I show you that very concretely with a case of a model with null forms. Right? The first in the first technical part that I have presented. So if there is only null forms, there is no metric coupling, then you get a uniform bound for the energy. Right? And so since there is a sharper estimate, sharper bonds, it's conceivable that the peeling estimates could be obtained in a wave gauge using the techniques like this. Thank you for being here.